Hello students, this is Professor Chilai, and in this video we're going to look at properties of crystalline solids. As always, you can follow along with our Chapter 10 workbook. By the end of this video, you should be able to describe bonding in crystalline solids. You should be able to relate the melting points in solids to the type of crystalline structure that they have, and also to describe defects in solid crystals. Let's get started. So far in this course, we spent a lot of time talking about gases. We've talked a little bit about liquids, and now we're going to move on to the solid state of matter and just talk briefly about how they come together. And when we talk about solids, there are generally two types that we can speak of: crystalline or amorphous. Right? So crystalline solids are basically those solids where the atoms or ions or molecules or whatever the solid is made up of, it appears in some repeating pattern. It's arranged in some repeating pattern. So it's solids where the ions or atoms or molecules, whatever it's made up of, are arranged in a regular repeating pattern. And I'll show you some examples of what I mean by this. But it's exactly what it says. There's some pattern that in the structure of the material that repeats. As for amorphous solids, it's quite the opposite. It's those solids where there's no real structure to it. Things just seem to be haphazardly placed, if you will. So sometimes these can be called non-crystalline solids. You might hear them called non-crystalline solids. And in these cases, the particles in these solids lack any order or internal structure. Basically, they're randomly arranged. Now, there we go. Now, we could study either of these, right? But because amorphous solids are randomly arranged, we're not going to go into too much about that, or at all, actually, for the rest of this chapter. We're going to focus on those solids that are crystalline, that have some pattern to them, and we're going to study those patterns. And in terms of the types of solids that we're going to study these patterns in, there are 4 types, as I list here: ionic solids, metallic solids, network covalent solids, and non-bonding molecular solids. And we'll talk about how those crystalline structures are ordered and what makes them up. In terms of what properties they have, they're listed here, and we'll go over a bit of that as well. Let's start with ionic solids. And here on the picture on the right gives you sort of an idea of what that might look like. But as we know, ionic solids are made up of ions, cations and anions. So let's say we're using the example of NaCl. So our example is sodium chloride, table salt, right? I'm going to use, same as the colors on the right, I'm going to use this purple color for sodium ions and the green color for chloride ions. And we know that sodium would attract chloride ions through electrostatic bonding, right? But this chloride could also attract another sodium ion. And that sodium ion could also attract another chloride ion. And I feel like you can see where this pattern is going, right? Maybe this sodium attracts another chloride ion over here. Maybe that chloride ion and that chloride ion attracts another sodium ion. And already you can start to see the regular repeating pattern that I was talking about. Or at least I hope you can. I'm not going to keep drawing this anymore, but this, I'm only drawing it in a 2-dimensional structure here, but this keeps repeating over and over again, and such is the nature of ionic solids. The bonds between them, these are ionic bonds, right, which we've studied. And so because of that, they usually have high melting points. So here's a 3-dimensional sort of structure of the same thing I was trying to draw. We have one ion here attracting another ion here, which then attracts another ion, and that sort of repeats over and over again. So that's it for ionic crystals. The exact shape of these sort of ions, the shapes that it can take, we'll look at that a little bit later. But for now, just know that in ionic crystals, the ions attract each other, and the pattern keeps repeating, right? In this example here, you can see that, for example, let's see if this pattern here, or let's use this pattern. This pattern repeats over here, and then repeats again here, and then it would repeat over here and over here. It keeps repeating over and over again. Hence the term crystalline solid. Okay, so that's it for ionic compounds. Let's look at metallic compounds. And here I'm going to use, I don't know, let's use the example of iron, right? Iron is a common metal. We know that metals tend to lose their electrons, and so what happens in metallic solids is you have some positively charged ion. Let's say it's, I don't know, iron 2 plus in this example, right? Lots and lots of those with all the extra electrons, and I'm going to use yellow for the electrons, surrounding them, sort of holding them together. This is my electrons. This is my C of D localized electrons. And so we can see it in a lot of metals, right? We have this sort of regular repeating pattern of iron followed by iron followed by iron. The atoms are regularly repeating. We call them metallic solids because they're made of metals. Because of this, the fact that we have this C of D localized electrons means that metals are good conductors of heat and electricity. It also lets them be bendable, right? Because these bonds, when you bend the metal, these bonds are not broken because they're not really bonds. They're just electrons that are sort of flowing around the ions. So metals can be bent, they can be stretched, and so on. And again, those properties are down here. You can read them up on them. But again, we classify them as crystals because oftentimes they occur in some regular repeating pattern. And here's sort of an example of that. All right, so let's look at network covalent solids now. Network covalent solids are, an example would be carbon, for example, diamond. But what it is covalent compounds that sort of infinitely repeat in some regular pattern. And they give you some example here, but think of diamond is this sort of carbon bonded to 4 other carbon, and that pattern repeats. This new carbon, let's highlight it orange now, would also be bonded to 4 other carbon, and basically every carbon is bonded to 4 other carbon, and so you get a infinitely, well, not infinitely because it must end unless you have an infinitely large diamond, but you have a very, very large crystal in which the pattern keeps repeating over and over. And remember, crystalline structures are one that has a repeating pattern. There are lots of other examples like silicon dioxide, silicon carbide, graphene. They're all compounds that are covalently bonded together, and with some repeating pattern, right? So I don't want to draw it because my drawing is not going to be as good as, you know, what you already see, but you get the idea that they're covalent bonds. So covalent bonds, and we know that covalent bonds are very, very strong. They're not easily breakable. So these materials, they'll be very hard. They won't conduct electricity because there's no charge to move around, and they would have very high melting points. Metallic bonds, they have variable melting points because they're some metals with low melting points, some with high. Ionic bonds are strong, so they will have high melting points as well. But covalent bonds will typically have the highest melting points of the set that we're looking at. And then finally, we're going to look at non-bonding molecular solids. These are solids where they're made up of individual molecules, and those individual molecules are held together using intermolecular forces, right? IMFs. And so an example here, we have iodine, right? These iodine molecules are all attracted to each other through intermolecular forces. In this case, it's all London dispersion forces. Water in ice form is a good example of that. So let me just write that. So for example, H2O ice, that's a solid, that's non-bonding. So if I were to draw water, here's my oxygen, let's use orange for hydrogen. Here's my hydrogen, hydrogen, right? We know that this water has hydrogen bonding, so this hydrogen will be bonded to some other oxygen, with hydrogen, hydrogen, and this sort of repeats, but it's held together by intermolecular forces, in this case hydrogen bonding. So it's going to be, those bonds are going to be much weaker than in network covalent solids or in ionic solids, and sometimes even in metallic solids, right? And that's why these substances, non-bonding molecular solids, would typically have very low melting points, like ice. Ice has a very low melting point. They have variable hardness, variable brittleness, and they typically don't conduct electricity. They're basically individual molecules held together by intermolecular forces. So those are the four types of crystalline solids that we're going to look at: ionic solids, metallic solids, network covalent solids, and non-bonding molecular solids. All right, so with that, how about you spend some time and try to classify each of these three as either ionic, metallic, network covalent, or non-bonding metallic molecular solids. Okay, let's look at gold. Solid gold. It's just made up of one kind of atom, but it's a metal atom, so we know that this would be a metallic crystalline structure or a metallic structure. CH3, 3CH2OH. This is, if we were to draw this, the Lewis structure, it would look like this, right? This is ethanol. Ethanol would sort of interact with other ethanol molecules. I'm going to try to make this as nicely as possible. It might not look nice. It's an H, through intermolecular forces, right? Hydrogen bonding. So H bonding. So if it's intermolecular forces, then we know that this should be a non-bonding molecular solid. All right, what about CaF2? We know that Ca is a metal, F2 is a non-metal, so this has ionic bonding. Ca has ion Ca2 plus, F has charge F minus. So this here will be an ionic solid. So there we go. We have a metallic solid, a non-bonding molecular solid, and an example of an ionic solid. All right, what about number 24? Spend some time trying to put these in order of from lowest to highest melting point. And then you can unpause and we'll go over it together. All right, so in order for us to figure out what their melting points are, we need to figure out what kind of solid they form, and therefore what kinds of bonds are holding them together. So MgO, that's an ionic compound, right? Mg2 plus, O2 minus. So this is ionic bonds. It's an ionic solid. We know that ionic solid typically have very high melting points. I2, right? This only has intermolecular forces, specifically dispersion. Same for krypton, doesn't form bonds, it's held together by intermolecular forces, again, dispersion. If I were to figure out how much dispersion each of these would have, I2 seems to be a larger molecule, so this will have more dispersion. So the one with the weakest bonds will have the lowest melting point. Remember, to melt it, you need to sort of break those bonds in solid. So the lowest melting point, I would say, would be krypton, followed by I2, followed by MgO solid, based off of the types of solids that they are and the types of bonds that they have. All right, and finally in this video, I want to talk about crystal defects. Now, so far I mentioned that crystals have a regular repeating pattern. So let's look at an example of iron, right? We'll have an iron atom bonded to an iron atom to an iron atom, and this will repeat forever and ever in all directions. I'm only going to draw a few of these. Actually, I can put solid bonds, that's fine. Solid, solid, there we go. Let's put a couple more. But almost no crystal structure in real life is perfect. There are going to be defects, as we call them, in there. And there are many different kinds of defects. So imagine these green dots, or whatever color that is, are some metal structure or some other crystals where we have the atoms regular repeating. Well, defects can occur in different ways. One, we could have an impurity that's a substitution. So, for example, instead of an iron, somehow another atom found its way in there. I don't know, maybe it's chromium, who knows, right? That's an example of a substitution impurity. There's also substitution impurity where the atom sort of disturbs the crystal because it's of a different size. So in this example, it's of the same size, so it doesn't really disturb the crystal structure. But here it does disturb the crystal structure, so that might be a different type of example. But they're both sort of impurities by substitution. There's also vacancy, where, for example, I don't know, an atom is just missing in a crystal structure, kind of like that. There's an empty spot right there. Doesn't really disturb the crystal structure as much, it's just a hole, a vacancy. And then finally, there's interstitial impurity, where another atom, usually a much smaller atom, somehow fits his way in between the crystal structure. So maybe we have, I don't know, a hydrogen atom, that's a small one, that somehow found its way in there, right? Entrapped by the crystal structure. That's another type of impurity. They all sort of affect the crystal structures, but a little bit in their own way. So here's some examples of crystal defects. So to reiterate, in this section, we talked about crystalline solids and amorphous solids. Crystalline solids are those that have a regular repeating pattern, and so it's the ones that we're going to look at for the rest of this video. For the types of solids, there are 4 types that we looked at: ionic, metallic, network covalent, and non-bonding molecular solids, all of which have their own types of bonds that are involved, and therefore their own properties that they would have. But each of them would have some regular repeating pattern because they all can form crystals. Here we have some of the properties of those, including their melting points, which depends on the types of bonds. We classified some simple solids as into either metallic, non-bonding, ionic, or network covalent. And then finally, we ordered some solids in order of melting point. Actually, not finally, but we did order some solids in order of melting point. And then finally, we looked at some defects in crystals, including impurities and vacancies. All right, that'll bring us to the end of this video. In the next video, we're actually going to look at the specific structures of various types of crystals. We'll see you then. Bye.